CosmoPalooza. Yes, thank you for coming to the second update of the first session of CosmoPalooza 2023. We set this up as a platform for collaborations to be able to convey updates to the wider community. My name is Anthony Kermeen. I'm a co-organizer and I'll be the moderator of this session. So we're pleased to have PFS giving an update. And with that, I'll hand it right off to Tomami. Please go ahead.
Well, thank you very much, Anthony. Let me share my screen. Okay, so I'm Tomomi Tsunayama. I'm a postdoc at the University of Arizona and also a co-lead of a cosmology working group together with Chang-Fun Han at Princeton Universities. And I will talk about the PFS cosmology program on behalf of the cosmology working group. So in this session, I will present the overview of the cosmology program with the emphasis of the three unique aspects of this program, which is wide redshift range coverage, high number densities, and synergy with HSC. And Alice Pisani will talk about void cosmologies, and Teppei Okumura will talk about intrinsic alignment. And at last, Takahiro Nishimichi, who developed Dark Emulator, will talk about recent progress on Dark Emulator 2. So PFS stands for Prime Focus Spectrograph, which is the name of the instrument, and will be installed to Subaru telescope, which has the largest prime field among all the 8-meter telescopes in the world. As shown in the image of the PFS instrument, PFS is comprised of prime focus instrument with fiber positioner system, metrology camera system, fiber system, and spectrograph system. And the focal plane is equipped with roughly 2,400 fibers over 1.3 square degree field of view. And the spectrograph system will cover from 380 nanometers to 1260 nanometers. And this near IR camera is a unique component of PFS, which enable us to observe high redshift emission line galaxies. PFS cosmology program will cover 1200 square degree and we will visit the same area twice with 15 minutes exposure time. We will measure redshift of roughly 4 million emission line galaxies from redshift 0.6 to 2.4. And with these emission line galaxies, our science goals are constrain some of the neutrino mass with a precision of 0.02 eV, measure the time evolution of the dark energy density up to redshift 2.4, and test the theory of gravity combining both clustering and lensing. And those science goals really emphasize the strengths of the PFS cosmology program. So for example, some of the neutrino mass constraints really take advantage of the high number density of emission line galaxies that we have, and measuring the time evolution of the dark energy utilize wide redshift range coverage, and testing theory of gravity is a synergy science case with Subaru HSC survey, which was the previous session of this CosmoPalooza. So for the first science goal, massive neutrino suppress the clustering amplitude on small scales, as shown in the left figure. So this figure is comparing the power spectrum with massive neutrinos and without massive neutrinos. And as you can see, it depends on the sum of the neutrino mass, the level of the suppression change. And PFS can achieve the precision of 0.02 eV on the sum of the neutrino mass by combining Planck, Bose, HSC, and PFS, which is shown in the right figure. And when I say like HSC, I meant like cosmic shear measurement from HSC surveys. And for PFS, we use both power spectrum and Howard spectrum and bispectrum. And one of the strengths of PFS survey is that we have high number densities, which means that we can actually push to smaller scales, say Kmax of 0.5 megaparsec. And by pushing to like 0.5 megaparsec inverse, we can actually push the constraints by 30%. And by achieving like the precision of 0.02 eV, this means that we can actually test whether neutrino mass hierarchy is normal or inverted, which predicts the minimum sum of the neutrino mass to be 0.06 eV for normal hierarchy or 0.1 eV for inverted hierarchy. And by actually confirming which hierarchy is the neutrino mass hierarchy, we can actually set a concrete target for the neutrino-less double beta decay experiment, which can test then whether neutrino particles are Majorana or Dirac particles. The second science goal is measuring dark energy density with 7% accuracy up to redshift 2.4. In particular, redshift range from 2 to 2.4 is PFS unique redshift range, where PFS is the only survey which can observe emission line galaxies at this point. And additionally, we can constrain omega matter and H naught using a single tracer. Here in the left figure, I'm showing the result from the both surveys doing the low redshift BAO measurement using galaxies and high redshift BAO measurement using Lyman alpha. And with PFS, we can actually go from redshift 0.6 to 2.4 using only like emission line galaxies. And DAISY will also measure the emission line galaxies up to redshift 1.6 and Lyman alpha above redshift 1.6, meaning that this will be complementary to DAISY. And also by combining low redshift probe and high redshift probe, we can really break the degeneracy between H naught and omega matter. And by combining those two probes, we can give tighter constraints. And the third science goal is testing the theory of gravity by measuring redshift space distortions, which is shown in the left figure, where we show that growth rate of the structure as a function of redshift. And red points are the forecast from the PFS surveys, and green is from DAISY year one. And the black line is a prediction from the general relativity, and blue dashed line is from one of the modified gravity models. So PFS is unique to constrain the growth rate of the structure above redshift 1.6. And another uniqueness is that the right figure with easy statistics. Easy statistics combine the clustering and lensing signal and can test the theory of gravity because clustering gives the kinematic information while the lensing gives the gravitational potential information. And blue and orange points are the constraints from the PFS when combined with either HAC lensing or ACT-CMB lensing. In addition, from the full shape analysis, we can also constrain omega matter and sigma 8. And this can really shed light on SA tension at redshift above 1. So currently, there is a tension between CMB and CMB lensing and the late time universe probe, which is a galaxy and cosmic shear lensing analysis, which is shown in this figure. And PFS can actually provide the constraints on S8 at high redshift. So we can really test how the S8 value is shifted as going from low redshift to higher redshift. So these are the three science cases from PFS And this is a summary, and I will leave this summary and take the questions. Thank you.
Thank you, Tomomi. Does anyone have any questions? You can put them in the Q&A. While we wait for a question, Tomomi, would you maybe want to go over your summary?
Yeah, so I think the ongoing galaxy surveys like DESI and Euclid really cover wide redshift. And for BL measurement, having like wide area. And having wide area is an advantage for BL measurement. But I think, and PFS covers 1200 square degree, which is 10 times smaller than DESI, roughly. But I think I'd like to emphasize by going to higher redshift, our science program can be really complementary to DESI and Euclid. And the PFS cosmology program will start taking the science, we'll start taking scientific data next year fall. So hopefully like we can have like enough data in similar timeline as DESI and Euclid.
A reminder that there is a Q&A feature people can submit questions to. If we don't get to them live, they can also be answered via text. All right, we do have one question. So what sort of target completeness do you expect for PFS? And how important is this for your various science cases?
So currently our survey design is such that we maximize the fiber efficiency rather than focusing on the completeness. So our fiber efficiency is above like 90%, but completeness will be like either from like 40 to 50%. But this science design can be changed based on our target selection criteria. We are still waiting for commissioning data to do the target selection to finalize. So it will depends. And completeness is important, but we also know how to correct and recover the underlying clustering of the target galaxies. So low completeness will not affect our various science cases.
Great, thank you. Could you maybe define those two terms you use, the fiber efficiency and the target completeness?
Yeah, so fiber efficiency meaning that we have 2,400 fibers, and high fiber efficiency means that we use most of the fibers to observe emission line galaxies. While completeness, it depends on the number of target galaxies which get fibers which get spectra divided by the total number of target galaxies. And one of the way to increase fiber efficiency is prepare more number of target galaxies than the available fibers. That's why having high efficiency usually leads to low completeness.
Great, thank you. We do have another question that was sent privately. So what is the observing schedule going to look like for PFS, and how often do you plan to observe? And then a follow-up is, when will you release data?
I see. So we are still currently at the commissioning stage and testing like various instrument performance. So we are having like those like science verification data in August and December of this year. I don't know whether we can make those science verification data public, but we will start actual survey in 2024, which is next year. And we will release the year one data once we publish the cosmology analysis based on the year one. So it will be maybe 2 years to make it public.
And roughly how many days a year will you be observing?
What do you mean, how many days?
How much will PFS be using the telescope? How many days per year will the survey be running?
Which is still like haven't finalized yet, but the PFS PFS survey itself is like 5 years survey, and cosmology program will use most of the night in the first 2 years.
Okay.
Yeah.
Okay, great. Thank you very much. I think we should move to the next speaker. That's Alice. Perfect. Could share your screen.
Absolutely.
Excellent. Please go ahead.
Thanks a lot, Anthony. So first of all, thank you, Tomomi, for this very nice introduction to the capabilities of PFS. In this presentation, I will shortly focus on one of the applications that we will be able to use from PFS data. My name is Alice Pisani, and I'm involved in PFS, in particular with a program exploiting cosmic voids. So what are cosmic voids? As most of you may know, cosmic voids are the underdense regions in the galaxy distribution. So we know that galaxy maps contain information way beyond the 2-point correlation function. And so cosmic voids are one of the techniques that allow us to try and exploit the galaxy maps beyond the use of the 2-point correlation function. So before talking a little bit more in detail on what voids can do, I'd like to give a hint of why we're interested in voids. So voids are underdense regions, and so by definition, they are dark energy dominated. So of course, if we want to understand dark energy, it makes sense to look into those regions. We also know that they're sensitive to diffuse components. So we expect a signal from neutrinos in the properties of cosmic voids. Voids are also expected to be sweet spots for testing gravity theories. And they are easier to model. So we can basically exploit traditional techniques, and models are actually holding their validity down to very small scales. Finally, voids are also a potential region to look at for a high signal to noise for dark matter. So those are our main motivations. But what do we do when we actually use voids, and why is this particularly interesting for PFS? When we look at voids, we're going to basically have the center of voids, and then we're going to look at the galaxy distribution around those voids. So we can look at different statistics when we look at voids. And so I will today mention a few of those. The first one is the void galaxy cross-correlation function. So looking at what is the probability of having a galaxy around a void center. So it's basically looking at the density profile. The second one is counting voids, so looking at the number density of voids. And the last one is the void autocorrelation function. So it can be understood as the probability of finding a void at a given distance from a certain void. So all these different statistics have been linked in past work, and this is definitely not an extensive review of all the works that have contributed into exploring these different statistics, but the voids have been linked to, as I was saying before, constraining some of the most important unknown in cosmology nowadays. And in particular, I will like to highlight a couple of recent results that are motivating us into looking in voids cosmology with PFS data. Because all of those statistics are not at the same degree of maturity, I will focus on the first two. The first one is the observed void galaxy cross-correlation function. In particular, I am showing here done in collaboration with Nieko Amaus. The idea is that we are able to have an extremely robust modeling of the void galaxy cross-correlation function, where we are accounting for the fact that, of course, we measure voids shape in redshifts. So velocities will distort our voids. So what you see in this plot is basically showing the galaxy cross-correlation function in white, and then a measure on Mach in black. And you see that we are able to model the void galaxy cross-correlation function with great precision, also at very small scales. This is a field that has been really, I would say, popular in the last few years. So 10 years ago or so, this plot did not exist, but nowadays we can actually the epsilon parameters, so the Alka-Pasitsky methodology, thanks to cosmic voids. And what this plot shows is how we are populating different redshift regimes. So from what we see here, voids are becoming extremely popular, and PFS will allow us to explore this same technique at much higher redshift. So opening an unexplored set of information which we haven't seen so far. Besides this, it will, of course, thanks to its high density, be extremely performant in terms of measuring the void galaxy cross-correlation function at the redshifts that are not very much explored so far. The second methodology that we can use with voids, as I mentioned before, is the void size function, so counting voids. This is also a relatively recent application to data. We have a robust model, and this is work led by Sofia Contarini on BOSS data. You see that we are able to find voids in the BOSS dataset from the SDSS survey, and we can see that the model overlaps pretty well with the measured points. So why is this important? Because, of course, it allows us to bring constraints. And in this particular slide, I would like to highlight a number of things. First of all, when we think about voids, we have different statistics. And of course, they will constrain the parameter space in different ways. So what this first plot shows is that you can, for example, combine void counts and void shapes to get a combination that is from cosmic voids that is, of course, tighter. But not only cosmic voids are powerful in terms of constraints, they are extremely powerful also when combined because they explore different orientations. Last but not the least, in this very recent work, voids have shown for the void abundance, so for the void numbers, to be able to contribute to the tension landscape. And even though the error bars are pretty large as of now, these are results that are obtained with only 6,000 voids. So before we step up to what can be done with PFS, I would like to highlight two more recent results. Very recently, Leander Thiel has led a work providing the first constraints from voids on neutrinos, which you can see in this plot. Again, even though those constraints are not powerful, they show that voids can contribute in a completely independent way to the probes that we have nowadays. And finally, this is work from Bonnie Yue Wang on using machine learning to exploit other void statistics, such as the ellipticity of voids that we currently haven't not explored with data. So all of this is work that has been done with, for example, current data set of voids that have 6,000 objects or so. But we can make a forecast with what PFS will give to us. And so PFS is expected, as Tomomi was mentioning, to have an incredibly high tracer density, and this tracer density will be maintained high enough at very different redshift range, so from Z.9 or so above and going above redshift 2. So we can measure, we can predict the number of voids that we're going to measure from the PFS survey, and this will give us of the order of 60,000 voids. So there is going to be an incredible gain in statistics. And I would like to highlight that not only we will have an incredible gain in statistics, but because of the high density of PFS, we're going to actually reach much smaller scales. So some of those models have been shown to be extremely performant in simulations when in extracting cosmology from the smallest scales, where physics becomes mostly nonlinear, and our model seems to hold down to a few megaparsec per H scales. So the idea is that this will allow us to extract constraints in a very performant way. And so this is work now from Giovanni Verta that has been exploring what is the expected void size function from PFS. What you see in this plot is, again, the void size function in the different redshift bins and the expected measurements that we will have. And we can then look at what this will look like in terms of constraints. So here in this plot, you see the expected constraints on dark energy, sigma 8 from cosmic voids. And in particular, this is really work that is only using the void size function. So within the collaboration, we are now moved to exploring all the different techniques. And the idea is to get expected values for PFF for constraints from other void statistics so that we can combine with the void size function and other standard tools. In the most interesting way, because of the hierarchical setup of the cosmic web, we also expect PFF voids to be extremely complementary with other surveys that will be happening at the same time. So just to move to my conclusions, void analysis is an extremely active field of galaxy clustering, and it actually involves many different statistics, each one with their own set of modeling and techniques. The prime focus spectrograph surveys will provide a unique data set of 60,000 voids, which will allow us to provide independent constraints on a set of cosmological parameters. And we expect this to be particularly interesting as a set of standalone constraints, but also in combination because of the way in which voids are orthogonal in their way of constraining cosmological parameters. And I guess I'll stop here and I'll take questions.
Great, thank you very much. Again, I invite people to enter their messages in the Q&A feature. Maybe I'll kick it off with one. So do you have any plans to do some sort of preliminary analysis with the SV data, or will you have to wait until the first survey data comes in order to start these works?
No, absolutely. The cosmology working group, and Tomomi can complement on this, is building up a set of simulations. And the idea is really that as of now, we're doing forecasts for constraints, but these constraints get, these forecasts get much more reliable, of course, if we have a real mock with all the details. One thing that we have been investigating is the impact of fiber assignment for voids. And luckily enough, it doesn't seem that it has a strong impact on our observables, such as, for example, the void size function. So definitely we plan to have some, first of all, a first set of forecasts that are similar to what I have been presenting today, but possibly including other void statistics. And then we plan to also extend this to a full analysis of a mock that will reproduce PFS observations.
I'll wait one more minute for more Q&A. And if we can't get to it live, there's always the opportunity to ask a question in the chat, and it can be answered offline in chat as well. All right, we did get one question, so let's see. Naive question: how do you estimate covariances with external 3x2 point probes?
That's an excellent question. So as a matter of fact, for now, the only solution is to have enough mocks and try to consider whether we can use those to estimate covariances. There is also some ongoing work into modeling those covariances with large set of simulations. One example is the Gigantes set of public void catalogs, which we can use for that. But of course, when we think of combining with other observables, we need to think of either performing the joint analysis on mocks or yeah, well, I guess that's the way to go. Yeah.
Great, thank you. Another question: will the analysis pipeline / ML tools be made public so that it can be tested on other data sets?
Well, I'm not sure what is the the decision for the PFS part, but we will have some tools at least for the generic void analysis that can be provided as public. We will abide, however, to what is done for the rest of the PFS analysis. But yes, if possible, we'll definitely like to make code public.
Great. Tamami, did you have a follow-up on that?
Yeah, and if someone's analysis tool which are uniquely developed in PFS, then those tools will be publicly available.
That's great. Thanks for confirming.
And then one last question. Is there anything that can be done to mocks/sims to get a significant improvement on your understanding of voids?
Definitely. I think that one of the things that the community is lacking nowadays is simulations that are both large enough and highly resolved on the smaller scales, so that we can actually test voids on their full breadth or on their full range of activities. This is actually true for most higher order statistics. So as of now, we play with the simulations we have, trying to go to the smallest scales, but of course, because we can go to as small a scale as possible with voids and try to extract information, and models seem to hold pretty well. If this could be modeled with simulations, that would be very helpful.
Great. All right, I think we should move on to the next speaker. Thank you very much.
Thank you. I'll stop sharing.
All right,
Okay.
Tempe, please take it away.
Yeah, thank you. Let me share the screen. Okay. Yeah, thank you very much for this opportunity. And I'm Tepe Okumura, working at Academia Sinica of Astronomy and Astrophysics. It's called ASIA, located in Taiwan. And yeah, I'd like to discuss about using galaxy intrinsic alignment as a cosmological probe using PFS. So this is a brief introduction, and as maybe everybody knows, intrinsic alignment is a coherent correlation between the shape of the galaxy with the surrounding large-scale structure like a filament. And it's known to be very serious contamination for the gravitational lensing survey, because gravitational lensing assumes the orientation of the galaxy to be randomly oriented, but yeah, galaxy shape has some particular preferred direction. But on the other hand, these days people discuss about the opportunity to use this as a cosmological probe, because the shape of the galaxy is correlated with the underlying density field. And it's a very schematic equation, but the galaxy shape is linearly related to the galaxy density field with some derivatives. And before talk about PFS, let me show you briefly about my latest work using Sloan Digital Sky Survey. And in this work, I analyzed this intrinsic alignment from the Sloan Digital Sky Survey data. And as I said, the galaxy shape is assumed to be linearly related to the underlying density field. So you have three statistics. The one is this conventional galaxy path spectrum in red space. So this PGG is a path spectrum in red space. So this factor is very well known, Kaiser factor, and this F is the growth rate. And since we have a shape field, so we have a cross correlation between the galaxy density with the shape, and this has a same Kaiser factor plus another factor coming from the shape field. So this 1 minus mu square reflects the fact that you observe the shape of the galaxy projected along the line of sight. And also, last one is a bit noisy, but it's also the autocorrelation of the shape field. And I measure those statistics and give a cosmological parameter estimations. And the blue contour is a result using only galaxy clustering. And the orange ones is the case that I combine galaxy clustering with its intrinsic alignment statistics. And I think the only important quantity is F sigma 8, and others are just nuisance parameters. And you can compare the orange contour with the blue ones, and you can see the the improvement is about 19%. And I analyze also other data sets, so not only luminous-red galaxy, but also LOSI and CIMA sample from both data. And sorry, it's a bit busy plot, but again, the blue point are the result from the only clustering, and the red one is the combination of clustering and intrinsic alignment. And the lower panel is showing the size of the error bar. So you can see the blue one is a error from clustering, and the red one always goes below the blue one. So that's the improvement. And maybe this improvement don't look very attractive, but here I'm using only the growth rate. But if you use the Algol-Patinsky, then of course this result will be a bit more changed. And I will show you some forecast results, including Algol-Patinsky later. Okay, so let's talk about the PFS and of course about forecast. So there are two important facts. So as Tomomi said in her presentation, the PFS has a good advantage that is we have a HSC. So we have very high quality shape information thanks to this imaging survey HSC. And another important fact is PFS is targeting emission line galaxies. And emission line galaxies are known to have a very small alignment with large-scale structure compared to elliptical galaxies. And these dot panels are demonstrating these two things. So y-axis is showing the figure of merit using clustering and intrinsic alignment divided by the figure of merit using only clustering. So the vertical axis showing unity means that you don't have any benefit using intrinsic alignment. Okay, and left panel is showing how this ratio depends on the shape noise. And the right-hand side is showing this same ratio as a function of the intrinsic alignment amplitude. So because we have a good shape quality, good imaging data, so actually the figure of merit of using intrinsic alignment goes rapidly up. But about the dependence on intrinsic alignment amplitude is a bit unclear because, as I said, the amplitude of intrinsic alignment for emission galaxy is quite small. And of course, if it's too small, then you lost all the benefits of using intrinsic alignment, obviously. And considering this fact, recently, Jinjin Shi a postdoc working at IPMU proposed a very interesting estimator of using intrinsic alignment as a proxy of halo shape. So she used the fact that most emission galaxies live in the very small halos and preferentially the center of halos. So she used the emission line galaxy observed by spectroscopic survey and also the light distribution around the emission line galaxies, and use this distribution as a proxy of the shape, the halo shape. Okay, so this is a demonstration of using illustrative T energy simulation, and she measured the power spectrum of intrinsic shape correlated with the density field, okay, as a function of the wave number. And it's a bit busy plot, but these blue points are showing the results if you naively use the shape of the emission line galaxy with correlated with the density field, and amplitude very low, actually almost consistent with 0 on linear scale. But if you use this information about the light distribution around the emission line galaxy, then the result become the red points. Okay, the amplitude goes up. And the gray points, so this is a simulation, so you can also measure the same path spectrum for halos. So she also measured the shape halo path spectrum, and they are consistent. This means that if this method works perfectly, then you can reconstruct the path spectrum or shape field of halos using emission line galaxies. Okay, so So simply saying, most pessimistic case, this amplitude of interest alignment 0. And most optimistic case, you can get the intrinsic alignment of halos. Okay, so considering that fact, again, let's look at a similar figure as before, but now the y-axis showing the improvement of constraint and constraint parameter as a function of, again, the intrinsic alignment amplitude. And I put this vertical lines that corresponding to the amplitude intrinsic alignment for halos. So we expect that our improvement will be between from 0 to this vertical line. Okay, and from left, I'm showing the result for F sigma 8 and Hubble parameter and angular distance. So roughly speaking, we can obtain between 15% to 30% if this method works perfectly. Okay, good. So, yeah, so this is the kind of a summary plot. So assuming this method works perfectly, and you can obtain the path spectrum of shape for halos, then this F sigma as a function of redshift, and this angular diameter distance and h of z as a function of redshift. And again, the black error bar is using only clustering, and the red one is after combination with intrinsic alignment. And you can constrain those parameters with a broad redshift. And if you assume the particular cosmic model, and this is the case that I allow dark energy to be time dependent, and you allow also deviation of gravity from the general relativity, and the curvature to be non-flat. And again, the contour, red contour is after the combined intrinsic alignment, and you can see clear improvement. So here I consider only growth rate and h of z and dA. And recently, the Kurita and Takada in IPMU use the same data set, strong distance survey data, and constrain the anisotropic non-gaussianity using the property that the shape field is a spin-to field. And also, there's another paper by a Chinese group in Shanghai. So they detect the BL signal directly from intrinsic alignment statistics, and it's published in Nature Astronomy. So this also show the future potential of using intrinsic alignment. Okay, so this is a brief summary. So I hope that I convince you guys that the intrinsic alignment is a good probe that complementary to galaxy clustering. And the power of intrinsic alignment is obvious for elliptical galaxy, but for emission line galaxy, it's still unclear. But we are developing some new method to utilize the intrinsic alignment from emission line galaxies. And if this method works well, then PFS can provide 15 to 30% better constraint by using intrinsic alignment. And yeah, I didn't talk about this, but yeah, neutron mass is very interesting, very important quantity, particularly for PFS survey. And we expect to have also the good constraint on neutron mass, but this is still ongoing work. Yeah, I'll stop here. Thank you.
Great, thank you very much. As with previous speakers, please put any questions you have for them in the Q&A. So maybe I'll ask the same question that was asked for the last speaker. Will the analysis pipeline for this be made public in some way so that people can test it on other data sets?
Yeah, I didn't plan that, but yeah, I think if I have a manpower, yeah, I think it would be nice, and yeah, it's good. Yeah, it can be useful for the community. But so far, yeah, I don't have many manpower, so yeah, I haven't considered yet.
Mm-hmm. Yeah, it would be presumably after the paper, so you you still have some. Very good, thank you. Are there any other questions? Give it 60 more seconds. I think it was just a very clear talk. Thank you very much. That was very interesting. We are at 9:15, so perhaps we move to Takahiro. Thank you again, Tepe.
Thank you.
Okay, let me try to share my screen. Is this working properly?
Yes, looks great. Thank
Okay,
you.
good. Thank you. So, hi everyone. My name is Takahiro Nishimichi from Kyoto Sangyo University. First of all, I'd like to thank Tomomi for letting me know about this opportunity, and I really enjoy this kind of sessions. And so this talk is slightly different topic, and we are indeed working with a quite small group of people, half independently to working independently to PFS. But so previously we worked on the Quest 1 project with a very tight connection with HSC people, and now the Quest 1 products are actually used in the pipeline in HSC. So I hope that the ongoing the Quest 2 project will be useful to people in PFS, but also for other surveys. Okay, let me start. So here is a brief summary of what is done in the Quest 1. So one line summary is that we performed simulations, N-body simulations to cover 101 WCDM cosmologies in six-dimensional parameter space. And based on the simulation data, we developed two kinds of emulator. One is for 2x2 point analysis based on Gaussian process. And this was so actually we models the dark matter halos, and the halo galaxy connection part was independently implemented as a HOD model, which can be changed if you want to update. So, and the dark emulator software is now public. And so now we have more than 10,000 downloads. And we can go to a smaller scale. So let's focus on this left figure. If you compare this large scale 3x2 and small scale 3x2, we can see that the constraint on omega matters S8 plane is tightened significantly by using small scale information, which is available thanks to this emulator. And another is to include redshift space distortion led by Yosuke Kobayashi now in Arizona. And this is a neural network based emulator. And we performed the full shape analysis of SDSS, both DL12 data set to put constraints on omega matter, sigmoid, or fundamental cosmological parameters. Okay, so here is a lesson we learned from previous experiments. So wide parameter coverage is crucial. So I compare here the Quest 1 parameters and two other recent emulator projects. And in this omega matter sigmoid plane, our coverage is quite wide. And you can compare this red box here with this HSE year 1 plus SAG SSDR 11 to cross 2 analysis. So this omega matter sigmoid plane. So our constraint is well within the DQ1 parameter coverage, while others are slightly smaller, maybe. And so even though we had to sometimes extrapolate the emulator prediction by using this simple linear scaling in the course of Monte Carlo sampler. But this is very rare. And if you see this full shape analysis, the blue box is quite small in this omega matter sigmoid plane. So this full shape information is very strong. So, okay, anyway, so wide coverage is important. Another lesson is this is from, again, full shape analysis based on simulation mock. And here we induced assembly bias effect in our mock by preferentially populating galaxies on halos with high concentration parameters. Even though dark emulator does not support or does not take into account assembly bias at all, we could recover these fundamental cosmological parameters without bias. So this is absorbed in some of the HOD parameters. So you can see, for instance, here, this vertical and horizontal lines are ground truth value, but sometimes you see the contours are slightly off. So this is what's happening when we analyze galaxies, which is affected by assembly bias. So the message here is that as long as we focus on pretty large scale, BAO or RSD scale, cosmology can be extracted pretty accurately. So this is another message. So given that, so what we are now trying to do is to expand the parameter space. Now we have neutrino masses. So this is one of the most important science targeting PFS. So also curvature, spatial curvature, as well as dynamical dark energy, WA parameter. However, expanding the parameter space is very demanding in terms of emulator building. So we want to be slightly more efficient. So instead of covering the standard rectangular shaped, hyper-rectangular shaped region, we target on this sigma 8 omega matter plane with this typical banana shape with width a bit larger than what we have from previous surveys. So now you can compare dark quest 1 parameter coverage. This is box, blue box. And so here, dark quest 2 coverage in omega matter sigmoid plane. Then, so this is compared with other emulator projects. So our emulator has slightly different shape, but in terms of omega matter sigmoid plane, we are covering pretty widely. And also maybe the plots are small, but we can compare one-dimensional parameter coverage, omega matter, omega B, blah, blah, blah. So red error bars are our dark quest 2 parameter coverage. And we can cover the mass, sum of the neutrino masses up to 0.5 electron volts, for instance. Okay, so to perform many simulations, we updated the simulation code. We newly developed a code called Ginkaku based on the publicly available library, FDPS, framework for developing particle simulators. And this is quite useful. We do not have to care about the efficient parallelization or domain decomposition or whatever. So this is automatically taken care within the library. So all we need is to implement force or time step and whatever. So and we basically based on Gleam particle mesh part plus standard bands hat tree. So it's a 3 PM code. And so this is accelerated by SIMD. And massive neutrino is implemented based on linear response method. So we do not solve neutrinos with particles, but we use the results of linear solvers. And so we multiply a boost factor to the Green's function to implement the neutrino impact. And this can be used to, for instance, deal with residual radiation perturbations or GR correction or whatever, clustering dark energy. So this is pretty useful. And so you can compare the performance. So our Ginkaku code scales pretty well down up to many CPU cores. And here you can compare our circle symbols are our fiduciary setup, and the triangle is slightly more accurate setup up from Ginkaku. So here is a comparison of the matter power spectrum using the public initial condition data made public by these people. And so you can compare that you can see that our results are pretty consistent with, for instance, Ramses. And if we use a high accuracy mode, red triangle, the result is very similar to PKD graph 3. Okay. And now we are trying to update it to perform well in supercomputers like Fugaku. So here I show the number of CPU nodes instead of cores. So you have to multiply by 48 to see how many CPU cores we use. And up to this many CPU cores, we can perform pretty well. Okay, so maybe I can not spend much time to fully explain this, but to be efficient, to make it efficient, we have a pretty involved architecture when we emulate the nonlinear power spectrum. And so the bottom line is that in addition to the cosmological parameters here listed here, we explicitly input the resolution of the simulation as a number as an input to this emulator. Also, linear power spectrum. This is also treated as an input to the nonlinear power spectrum emulator. And this helps to for instance, have a better generalization ability, because even if we do not have a nearby cosmological parameter, we can safely make a prediction for the linear power spectrum, which tells you approximately how the nonlinear matter power spectrum should behave at that cosmological parameter sample. And also by aligning resolution as an input, we achieve the mixed resolution dataset. So running based on a mixed resolution dataset. So we have 3 layers of simulation data. So we have many low resolution simulations plus 100 mid-resolution data plus 40 high-resolution data. So these are coherently treated in this network. So now our emulator can make a prediction given resolution or number of particle. So if the resolution is this big, what is the expected power spectrum, and vice versa. Okay, so let me continue. And so we are based on standard feed-forward neural network, but the hyperparameter space is pretty huge. So we decided to use some automatic way called CMAES. So now, so this is just a cartoon figure. So suppose we are within this circle. So we try some samples in this circle and just select the best performing ones and make another circle. So this we call generation. So now after 40 generations, we end up in a quite shallow network with many neurons each. And this was a kind of optimal setting. And now so I'm showing the power of this mixed resolution dataset. if we study the nonlinear matter power spectrum using only the low resolution data compared to higher resolution data, so we have some systematic residual here, like here. However, as we increase the number of, in this case, mid-resolution data, the residual soon get closer to zero. And here, how many? So we can see that about 40 mid-resolution data is already kind of satisfactory. And with this emulator, we can now very easily make a prediction for this typical damping due to massive neutrinos, for instance. Okay, so finally, let me show. So that's not the end of the story. So comparing. So I'm not trying to be offensive to anyone. So I just hide which emulator they are. But compared to the publicly available emulators, the power spectrum residual is not so small. Nobody is within 1% compared to ours. So because we are still preliminary, I'm not saying that our emulator, the 0 point here, is the ground truth. So maybe we are wrong. But so the message here is that we are not really converged. And also some of the residual are tightly correlated with cosmological parameters. For instance, here, color-coded by neutrino masses. Okay, maybe time is up, so I stop here. Thank you for your attention.
Thank you very much. Thank you very much. While still keeping which plot is which blinded, could you tell us the three that you're comparing against?
Sorry, say again?
In your last slide, could you just tell us the three that you're comparing against? You don't have to tell us which is which.
Yeah.
What are the three emulators?
So okay, so we have three emulators here. One is Bakko Emu, another is Miller Titan 4, and the other is Euclid Emulator 2. But I don't tell which is which.
Yeah, we won't know which is which. Great.
But you can see, you can guess from this parameter coverage if you want.
Okay. All right. Thank you very much. For the sake of time, maybe we'll take the remainder of the questions in the chat. Do you have a few minutes to stick around in case people have questions?
Okay.
Great. Thank you very much. And thank you to all of our speakers. Thank you to PFS for providing the speakers and joining us today. I think it was a great session. And thank all of the attendees for joining. And we will see you again tomorrow. Yeah, let's give a virtual round of applause. Sorry, I should have done that earlier. Virtual round of applause for all of them, all of our speakers. All right, we will see you tomorrow at the same time to hear from Euclid and Shoes.